Now that we've simplified radicals, we're going to start looking at different operations we can do with radicals, such as multiplication, addition, and subtraction. So before we look at these rules over here, let's look at some examples of them and see where we can go. So if I did the square root of 2 times the square root of 3, we've kind of mentioned already that we can break apart radicals whenever we simplify them and turn them into two separate radicals that you're multiplying. The same thing applies here. I can do this 2 times 3 on the inside of the radical and make this the square root of 6. If we then had an example like the next one where we have coefficients on the outside, we're going to multiply the 4 times 5. Those are more of the rational numbers, and the 3 times 2 on the inside because they are the irrational numbers being inside the radical. This will simplify to be 20 square root 6. Now the 20 has nothing to do with the radical. It's a number just on the outside. We're not going to have to worry about simplifying it. It does not involve the 2 or the 3. We leave them separate. The exception to that would be if you could simplify the square root of 6, you need to make sure you simplify that and bring the values out to the 20. The last one here is the square root of 3 times the cube root of 2. This one cannot be simplified. Now, that doesn't mean it's not correct. It's just already in its most simplified form. They're not the same index. They must have the same index whenever we multiply the radicals together. All of these were square roots. They gave a square root result. All of these would be square roots. They'll give a square root result. So as we go through, make sure they have the same index. They could both be cube roots, fourth roots, fifth roots, whatever. They just need to match. So we come over here. Anytime we have the square root of a times the square root of b, it's going to be the product on the inside, the square root of a times b. And then we'll multiply the outside numbers and the inside numbers. This is all very similar to the simplifying you've seen in simplifying radicals, and it'll just be a continuation from that. Now addition is a little bit different. So if I looked at the square root of 3 plus the square root of 2, if I think of the square root of 3 almost like a variable, it's a constant term, it is a value, but what I'm saying is I have 1 square root of 3 plus 2 square roots of 3. The same way I would say I have x plus 2x would give me 3x. Here, this gives me 3 square root 3. The radical stays the same. It's the coefficient that changes. So 1 plus 2 would give me 3. For example, now at 5 root 6 plus 4 root 6, we can say that's 9 root 6. The root 6 stays, it does not change, it stays the same. It's the coefficients that we add. So then if we look at something like the square root of 12 plus 3 root 3. At first it looks different, but this is where we have to use our simplifying to help us. And whenever we add or subtract with radicals, we're going to have to simplify the radical first before we can make sure we can add. And why we do that is 12 is 4 times 3, which has 4 as a perfect square or a set of 2's. So this actually becomes 2 root 3 plus 3 root 3, and we get 5 root 3. Make sure you can't simplify further to see if they can actually match. So we come over to some general examples. The square root of a plus the square root of b cannot be simplified. And the reason for that is they do not have the same radical on the inside. If it was multiplication, that's fine, but addition, they have to be the same. Whereas if it's the square root of a plus the square root of a, you're going to say 2 square roots of a. If I have different coefficients, kind of like I had on this example, you're going to say it's x plus y times the square root of a. You're not changing a, it stays there, it's the coefficients you're adding. The last one, the square root of a plus a square root of b, also cannot be simplified. And the reason being it does not have the same value in the radical. Now again, this is not that these are wrong and they're false or you're saying no solution, they're just already simplified to their final form, and that is perfectly fine. Don't force them together. So let's look at some examples of that. We'll first look at a multiplication. What I would usually do in multiplication is regroup to one radical. It's really tempting at times to start to simplify what's inside of each radical and then try to put them together. For example, we're looking at 60, saying, well, what perfect squares can I find? Or the x's and y's. If we put them all in one radical, then you're only simplifying one thing and you're not having to do two separate things and maybe lose terms as you go through. So regroup into one radical. Now look for sets or perfect squares. What's nice about what I've done so far is I have not multiplied 60 and 15 together, and I can use that to help me, because if I need to find perfect squares and I'm not originally given a perfect square, I want to find sets that are already factored. It'd be really nice if I could get a 15 out of 60, because then it pairs with the 15 I already have, and I do, because 4 times 15 is 60. Furthermore, 4 is 2 times 2, so we actually already know what values are going to factor out. So it's going to be a 30 on the outside because we have 2 times 15. The other way you could have done it is you could have multiplied 60 times 15 here, and you would have gotten 900. The square root of 900 is 30, so you'd get there either way. Now we look at the variables. X to the 5th. There are 5 x's there. There are 2 sets of 2, so 2 come out, with 1 left over, so that stays in. Y to the 3rd has 3 y's, that's 1 set comes out, 1 left over. So our answer here is 30x squared y times the square root of xy. Now as we look at addition and subtraction, we must have the same radical and variables with exponents. For example, right now I have x square root of 16x to the 3rd, and I have square root of x to the 5th. Those do not match. They need to be exactly the same if we're going to combine them together. Kind of like what we did up here with square root of 3 and 2 square roots of 3. So I got to simplify them down first. So this one we're going to simplify before we put them together, whereas multiplication, we put them together, then simplified. Just a different approach. So let's look at negative 3 square root of x to the 5th. Well, x to the 5th is 5 x's. That's 2 sets of 2 that I could take out. So that's going to be negative 3x squared square root of x. If I can get the first term to have x squared square root of x, I'm in good shape and I can combine the two values. So now if I look at it a little bit more, I got x square root of 16x to the 3rd. Well, I know 16, the square root of that is 4. So that's going to come out. X to the 3rd has 1 set coming out. To go along with the one that's already there becomes x squared square root x. And lo and behold, they match. So now all we're left to is subtracting with the coefficients. Same thing we did up here. 5 and 4 became 9 because it was addition. 4 minus 3 down here is going to become 1 x squared square root x, or just write x squared square root x. So let's go through some different examples, and we're going to jump between multiplication and addition just to make sure we're following the rules correctly. So square root of 24 plus the square root of 72. We have to simplify the radicals first before we can see if we can combine. 24 is 4 times 6. 4 being a perfect square is going to make it into 2 root 6. 72 is 36 times 2, which gets 6's out. You could have factored it differently, but as long as you get to 6 root 2, you're on the right track. So these are our 2 simplified radicals. We look to combine them, but they don't match here. That's fine. This is our answer. As we move over and look at the 4th root of 81 plus 5 times the 4th root of 81. 81 is 9 times 9, which is 4 threes, we should say. Now that works for both of them. So if we're looking here, the 4th root here, I can take out a set of 3's, so this whole thing becomes 3. Same thing applies there. That whole thing becomes 3. Now following just basic order of operations, 5 times 3 is 15. Bring down the 3. Our final answer is 18. Now you may be looking at going, well, why didn't you just do this term plus 5 of these and make it 6 4th root of 81 to start? It still would have worked out because that became 3 and we still arrive at 18. Either way. So now we look at the next one. It's now the cube root of 81 in both of them. So why don't we do that first here? Let's make it 6 cube root of 81 because, well, they already match. So 81 we've said is 4 threes. So I'm going to take 1 set out, so that's 6 times 3 on the outside, and the cube root of 1, 3 left over. We have to make sets of 4. We didn't have an exact set, or sets of 3. We didn't have an exact sets, so we got a leftover. Last thing we do is 6 times 3 gives you 18 cube root 3. On our next one, it's a multiplication, so similar to the ones we saw on the front page, we're going to put the outside terms, the coefficients, together. So that's 5m times 2, and then put the rest of it inside a radical. So I have 48 and 27. 27 sticks out because that's 9 times 3, and I get a set of 3's. 48 is 3 times 16, which also pairs up a set of 3's. And 16 is 4 times 4, which has a set of 4's. So now I kind of know which numbers are coming out. I got a 5 times 2 times 3 times 4 times another 3. Now for variables, I already have an m. That's on the outside. M squared inside the radical is going to bring another m out. N to the 6th inside the radical is going to bring 3 of them out. So everything gets taken care of. There's no radical left over. Now we have to put it all together. So 5 times 2 is 10. 3 times 4 is 12. Times 3 is 36. So 10 and 36 gives me 360. Then I have m squared n to the 3rd. On to our next one. We have a cube root of 100 times 54 x squared, and an x squared gives me x to the 4th and y to the 8th. So it's cube root. So 10 and 10 probably aren't going to work. I got a 2, a 5, a 2, and a 5. 54 is 2 times 27, which is 9 and 3, and I get some 3's there. So let's look at what sets I have. Here's one set of 3's. That's coming out. I have a set of 3 2's. That's coming out. And what I'm left with on the inside is 5 and 5, which is just 25. If I had a third 5, they would all come out. Unfortunately, I do not. Now we got x to the 4th. X to the 4th has one set of 3's. One stays inside. Y to the 8th has 2 sets of 3's, because that's 6 of them. 2 stay inside. So now when we put it all together, we got 6x, be a 2 there, 6xy squared, cube root of 25xy squared. Don't forget the cube root. Last one we have here, we're going to subtract, which is similar to addition. We have to make sure they do match. So let's start working with what we have. 40 is 8 times 5. I know 5 is a cube root, which will give me a set of 2's coming out. So 2's come out. Along with the x that's already there, I get another set of x's with 1 left over, so 5x stays inside. So this is 2x squared, cube root of 5x. 135, I want a 5. If I can get a 5 somewhere in here, I'm in good shape. So if I divide that by 5, it's actually 27. 27 is a perfect cube. So this is going to become, 3 comes out, 2 x's come out, 2 sets, so I got an x squared there, cube root of 5x. Bring down. Well, we check if it matches. It does. X squared cube root 5x, it matches at whatever, however complicated it is, but it comes down to 2 minus 3 is negative 1, x squared cube root of 5x, or negative x squared cube root 5x. Either would be acceptable.